everyone, welcome back to Lulumath. This video is on finding an equation of a real-life quadratic relation, and this is the first video on this information. You'll need to know how to find the equations of quadratic relations in vertex or in factored form. So you can either use vertex form if given the vertex and another point, or you can use factored form if given the roots and another point. This video does not assume that you know how to solve quadratic equations yet, as this video comes before the lessons on quadratic equations. Later, when we do some lessons on quadratic equations, there will be more videos on real-life quadratic relations. All right, let's get right to it. A ball is thrown from an initial height of 1 meter. So this is key information that's going to help us out, and reaches its maximum height of 6 meters after 1.25 seconds. We want to write an equation to model this situation. Well, first of all, we need to identify what our variables are. Well, our ball will be following a certain path where it's going to go up and then it's going to reach its maximum point and then it's going to come down, and the height will depend on how long it's in the air for. So our two variables are the height and the time. But since the height depends on the time is our independent variable. So we're going to say let the time in seconds equal x, and then we'll say let the height in meters equal y. And just a reminder that this is the independent variable and this is the dependent variable. Now, we want to draw a rough sketch of what's happening in this example here. So because time is the independent variable, we'll put time here in seconds. And because the height is the dependent variable, we'll put the height here in meters. And this is 0. And since it reaches its maximum height after 1.25 seconds, I will go to 3 seconds just so I can maybe hopefully get a good picture of what's going on here. And since my maximum height is at 6 meters, I will go up to about 8 meters just so I can get a good picture of what's going on. And this line right here represents the time of 1.25 seconds where my ball will reach its maximum height. And that maximum height occurs at 6 meters. So here, this point represents my maximum or my vertex, and the point is 1.256. Now, I also know it has an initial height of 1 meter. At the beginning, when it was initially thrown, my ball starts at 1 meter. So this is the point 0.01 because this happens at 0 seconds. Now I'm going to draw just a rough sketch of the path that the ball takes. We're going to try to make this as symmetrical as possible, but again, it's just a sketch. So my ball is thrown from a height of 1 meter, it goes up, it reaches its maximum height, and then it comes back down. So since we want to write an equation to model this situation, we have to understand that we are given the vertex, which means that we will want to use vertex form. And vertex form is y equals a times x minus h quantity squared plus k, where hk is our vertex. So here we know our h value, the x value in our vertex is 1.25. So that will go in for this h right here. And we know that the k value is this 6 right here, the y value. So we'll put it in for the k here. So it will look as follows. We'll keep the y, we'll keep the a, we'll keep the x. And then instead of h, we're going to say minus, and then our h value here is 1.25. But that's being squared, and then we're still going to say plus, and then our k value here is this 6. Now, just a reminder that we have to substitute a point in to solve for a. And the other point that is given to me is this point of 0, 1. So 0 represents the x value, and 1 represents the y value. So I will replace that information in to be able to solve for a. So I'll put the 1 in for the y, and I'll keep the a as is, and I'll put the 0 in for the x, and then I'll copy the rest of this equation down exactly how I see it. So now let's go ahead and just evaluate. So 0 minus 1.25 is negative 1.25. And I'll copy the rest of my equation down. And then negative 1.25 squared is 1.5625. And I can put the A after. It doesn't matter what order I do it in, so I'm going to put the A after, so I have this 1.5625 as a coefficient, plus 6, and then I'll copy the 1 down. Get rid of the 6 by subtracting it. So when I subtract the 6 from both sides, I end up getting -5 equals 1.5625a. Divide both sides by 1.5625, and I end up getting a equals -3.2. And I can replace that -3.2 in for the a right here. So this is what we had before without knowing what a is, but now that we know what a is, we can replace the a with this -3.2. So I end up getting y equals -3.2 times x minus 1.25 quantity squared. And then I've got a plus 6. And this is my final answer. This is the equation that models this situation. Let's use Desmos to verify that this is an actually correct equation. So we got y equals -3.2 times x minus 1.25 squared plus 6. So if we take a look at what we have here, we can see that it was initially thrown from a height of 1 meter, because at 0 seconds it's 1 meter, and it reaches its maximum height of 6 meters at 1.25 seconds. So this appears to be a correct equation. Excellent. So now this next question says that the ball was thrown from an initial height of 1 meter. When is another time the height of the ball will be 1 meter? Well, let's take a look at our graph that we have here one more time. So we know initially it has a height of 1 meter. So I want to know, when is it going to have a height of 1 meter again? So when I extend this line here, I can see that this is where it's going to have a height of 1 meter again. We can see that it appears to be around this time right here. However, this is a rough sketch, so we don't know for a fact that that's exactly the correct value. So we have to think of other ways to get an accurate answer. Now we've got two options. We can either solve a quadratic equation, which this video assumes that we don't have that knowledge quite yet. We can revisit that idea later on when we have that knowledge, or we could use the idea of symmetry. So we know from this initial height of 1 meter to this maximum height of 6 meters that this took 1.25 seconds. So then by using symmetry, we also know from the maximum height to when it's 1 meter again, it will also be 1.25 seconds because quadratics are symmetrical. So based on that, altogether, these two values will add up to 2.5 seconds. So therefore, the ball will be 1 meter above the ground again after 2.5 seconds. Let's verify this information using the equation that we figured out. So what I will do is take this 2.5 and I will replace the x with 2.5 seconds. And then I will evaluate and see what I end up getting for y. Well, 2.5 minus 1.25 is 1.25, and 1.25 squared is 1.5625, and -3.2 times 1.5625 ends up giving me -5, and -5 plus 6 is 1. So I can verify that it really will be 1 meter above the ground after 2.5 seconds. Another option that we have is to go to Desmos and graph out the line y equals 1 and see where it will intersect with my quadratic relation. So it intersects at 0 seconds, which is expected because we knew that was going to happen, but it also intersects at 2.5 seconds. So there is another verification or another solution method that we can use to help us determine at what point in time it will again be 1 meter above the ground. All right, that's it for this video. If you have any questions, let me know in the comments below or at lulumath.com, where you can also find blank or completed notes for this video. If you found this video to be useful, please make sure to subscribe and to share with others. Thank you, and we'll catch you next time. Bye.